prime number is defined to be a number such that it is divisible only by 1 and itself. Prime numbers pop up almost everywhere in mathematics and are useful in many different ways, but what exactly makes them so special? To clarify, let's look at some examples where prime numbers play an important role. For example, in cryptography, the security of the RSA encryption relies on the fact that factoring large numbers into primes is computationally hard, even though uniqueness ensures there is only one answer. Without uniqueness, encryption would be unreliable. In computer science, prime factorization underpins hashing. Prime numbers also play an important role in error-correcting codes such as QR codes, CDs, or satellite communication. Within the framework of mathematics, primes are used to directly compute the least common multiples and greatest common divisors of numbers. They are also commonly used in irrationality proofs. For example, the square root of 2 is irrational because if 2 were equal to p over q squared, then both p and q would have an even number of prime factors, leading to a contradiction. They are also used in algebraic number theory, where classifying number fields often studies where unique factorization holds or fails. The two key takeaways mentioned above are factorization and its uniqueness. Factorizations is just splitting numbers apart into components such that multiplying all components together gives you that number again. For example, 25 can be factored as 5 times 5. As we've seen in our example, we really want numbers to have the property that they can be factored into prime numbers in a way that is unique, meaning that we can split up any number into prime numbers that multiply to that number, and there's only one unique of those factorizations, so there's only one set of numbers that factor any n. This is called the fundamental theorem of arithmetic, and it states that all natural numbers greater than 1 can be factorized into prime numbers such that this factorization is unique. This statement seems like complete magic, so let's actually see why it's true. The first part of the FTA is that each n can be factored into finitely many primes, so let's consider some n. Let's consider what happens when we factor n. We immediately know that both 1 and n are factors, since 1 times n is n. Those two factors we will call trivial factors of n. The immediate question that comes to mind is, does any number have non-trivial factors? This is obviously false, since primes are, as you may recall, defined to only have trivial factors. But does any non-prime number have non-trivial factors? We know that any number has trivial factors, and we also know that any prime is prime if and only if it has only trivial factors. So if n isn't prime, then it isn't only divisible by 1 and n, but must at least be divisible by another number or more. So let's actually factor a number and see what happens. For that purpose, we consider the number 84. We see that 84 has factors 2 and 42. If we now look at those factors again, we can see that 2 is prime, so we can stop, and we see that 42 equals 2 times 21. We see that 2 is prime, so we can stop again, and see that 21 is 3 times 7. Both of them are prime, so we can also stop. Now, the prime factors are the leaf nodes of this tree diagram. Stopping at primes really just means that we can't factor them non-trivially anymore, so it wouldn't make sense to break apart those factors further. Let's now formalize this notion. Let f of n be defined such that f of n is just all k that divide n, so f of n really just contains all factors of n. Further, we say that if we apply f to any set, we just apply f to all the elements of the set. Further, let not p of a be defined on a set A such that not p of a is just all a in A such that a is not a prime number. If we now apply f to any number n and then apply not p to it, then this set contains all non-prime factors of n. This set is now equivalent to the first rank in the tree diagram we constructed. If we now keep applying f and not p in alternating order, we will end up going through deeper layers of the tree diagram. With that in hand, we can define a sequence. Let a0 be f of n, which is just all initial factors of n. Let a1 be not p of f of n, which is just all initial non-prime factors of n, and let a2 be f of not p of f of n, which is just all factors of the initial non-prime factors of n, and let a3 be not p of not p of f of n, which is all non-prime factors of the initial non-prime factors of n. This sounds very complicated, but just familiarize yourself with the definitions of f and not p and work through the example again. Now if we remove a1 from a0, we see that this operation leaves us with all initial prime factors. Equivalently, removing a3 from a2 will leave us with all prime factors of the sub non-prime factors. We can now consider any a sub 2n minus a sub 2n plus 1 to get any prime factors of the 2n minus 1th subfactors of n. Since a non-trivial factor of any number must be smaller than this number, there will be a point at which we have a sort of convergence, and a sub 2n minus a sub 2n plus 1 will return the empty set. Now we are ready to construct a prime factorization. We define the prime factors of n to be p of n such that p of n equals a0 minus a1, which is just the first order prime factors, adding a2 minus a3, which is just the second order prime factors, and we keep on adding infinitely many orders of prime factors until at some point it's all empty sets, so nothing really changes and we get our whole prime factors. To tie it back to our tree diagram, this is equivalent to adding all the leaf nodes up until there's no leaf nodes left, so we're just done. If you remember those multiplication pyramids from elementary school, prime factorization is basically playing this game but in reverse, extending the pyramid until you can no longer extend it. So this essentially shows us that you can construct any number from a set of prime numbers. So primes are the building block of numbers. Now for the second big part of the theorem, uniqueness. So now let's consider what would happen if we indeed had two prime factorizations. Our first prime factorization is n equals p1 times p2 times p3 and so on for all its prime factors. We consider what would happen if there indeed was another factorization, n equals q1 times q2 times q3 and so on for all its prime factors. Now since n is equal to both of them, we can just write them to be all equal, and if we divide n by n, we just get that the one prime factorization divided by another prime factorization still needs to be 1. Now if we cancel out each p and q where p equals q, we should be left with some fraction that still contains some p's and q's, since we assume that both factorizations are in fact different. So after cancellation, we should still have some fraction p1 times p2 times p3 and so on over q1 times q2 times q3 and so on, which equals 1, which of course is equivalent to saying that those two are equal. In this equation, every q must be different from every p since we cancelled out all p and q where they are equal. Since both terms are equal, it must be the case that if we divide the second term by some p from the first term, we get that p divides the whole second term. Since we can do this for every p, we can see that pi, so any p, just divides our whole q factorization. Now consider what happens when any product is divisible by a prime number. If a product AB is divisible by some prime p, we know that AB equals pk for some k. Now if A has a factor of p, then obviously p divides A, since we can represent A as being equal to some multiple of p, and therefore p divides A. Now if A has no factor of p, the only way AB can be equal to pk is if p divided b. So if a prime number p divides any product AB, then either p divides A or p divides b. Going back to the fact that any pi must divide the q factorization, we can now see that either pi must divide q1 or pi must divide the rest of the equation. Similarly, now pi must either divide q2 or the rest of the equation. We can keep on going and see that pi must divide q1 or q2 or q3 or any q. But since pi and all q are prime, and pi can't be equal to any q since we did our cancellation earlier, we can now see that pi can never divide any q. So our assumption that the two factorizations must have been different is false, and we arrive at the conclusion that any factorization is in fact unique. With that, we have now proven the fundamental theorem of arithmetic. As always, rewatch the video if you didn't understand what's going on the first time around, as math is pretty hard to get into and my videos are always a bit on the shorter side. Anyways, if you liked what you watched, I would appreciate it if you could like and subscribe.